Welcome to this explainer. You know, if you've ever stared at a piping spec sheet and just wondered how all those random numbers, letters, and schedule designations actually translate into the physical piece of metal sitting right in front of you, well, you're in the right place. Today, we're going to totally crack the code on ASME B36.19. We'll break down everything you need to specify stainless steel pipes with absolute confidence. Let's get right into it.
Okay, I want to hook you right off the bat with this really fascinating tidbit from an Atlas Steel's tech note. Check this out. The dimensions of pipe are shrouded in the mystery of an arcane designation system. Its origins go back to ASME recommendations of 1886. I mean, think about that for a second. You could be specifying a highly engineered modern stainless steel pipe for a state-of-the-art chemical refinery today, and you're essentially speaking a dimensional language that was established over a century ago. Wild, right? So let's start by looking into the mystery of pipe sizes and why, say, a 2-inch pipe isn't exactly 2 inches.
If you actually take a tape measure to a standard 2-inch pipe, you'll see pretty quickly that it doesn't measure exactly 2 inches. Historically, standard pipe sizes were based on a rough internal diameter. But as manufacturing evolved and we needed different wall thicknesses to handle much higher pressures, that outside diameter had to stay standardized. Why? So that fittings and flanges would always match up perfectly. Because of that, the inside diameter shifted around and that original 2-inch measurement became nothing more than a nominal pipe size, or NPS. Basically, it's just a name now, not a literal physical measurement. So, to navigate this and find the true physical dimensions, we rely on our ultimate decoder ring, the ASME B36.19M standard. It explicitly defines outside diameters, wall thicknesses, and schedule numbers specifically for seamless and welded stainless steel pipes. If you're working with stainless grades like 304 or 316, this document is literally your engineering Bible.
But hey, before we dive too deep into the numbers, let's test your knowledge with a quick question about that naming convention. What exactly do you think that M at the very end of ASME B36.19M stands for? Take a guess.
Well, the M actually stands for metric. Yep, it means that metric units, specifically millimeters, are the primary units used for the actual physical dimensions inside the standards tables. Now, I know this can feel incredibly counterintuitive because out in the field, we almost universally refer to sizes using the standard nominal pipe size system, right? Like calling it a 12-inch pipe. But open up the standard itself, and all that precision is handled in metric.
Moving right along, let's look at carbon versus stainless steel, where we have two standards, but one really critical divergence.
Understanding the relationship between stainless and its older carbon steel sibling is exactly where a lot of engineers make critical and honestly sometimes very costly assumptions. See, we actually have two parallel standards running side by side here. ASME B36.10M handles welded and seamless wrought steel pipe, so primarily your carbon and alloy steels. On the flip side, ASME B36.19M is your go-to standard specifically for stainless steel. A really handy trick to know which one you're looking at is the S suffix. When you see Schedule 10S, 40S, or 80S, that S stands for stainless, tying it directly back to the B36.19M standard. Now, because these standards overlap in so many sizes, people naturally just assume they're completely interchangeable. Spoiler alert, they are absolutely not.
And this right here perfectly illustrates the danger zone. Just look at the 12-inch nominal pipe size mark. If you order a 12-inch Schedule 40 carbon steel pipe, its wall thickness is 0.406 inches. But if you order a 12-inch Schedule 40S stainless steel pipe, the wall thickness is only 0.3125 inches. The stainless pipe is surprisingly thinner. The exact same drop-off happens when you compare Schedule 80 and Schedule 80S. If you blindly substitute a 40S stainless pipe into a system designed for a standard 40 carbon pipe pressure rating without double-checking the math, man, you could be setting your system up for a catastrophic failure.
Okay, so let's get into cracking that schedule code and actually deciphering the numbers behind the steel.
Have you ever actually stopped to wonder why it's called Schedule 40 or Schedule 80? It's definitely not some random categorization they just pulled out of thin air. Schedules are actually derived from a very specific engineering formula: 1,000 multiplied by P divided by S. In this neat little equation, P stands for the internal design pressure of the system, and S is the allowable stress of the specific material you're using. So this formula is basically the mathematical proof that higher schedule numbers will always mean thicker pipe walls to handle greater pressures. Makes perfect sense, right? But hey, defining the thickness on paper is really only half the battle. Actually manufacturing it consistently, that's the other half.
When you look at an actual specification chart, you really get a sense of how rigorous the allowable wall thickness variations and testing tolerances truly are. Depending on the exact ASTM standard you're using, whether that's A213 for boiler tubes or A269 for general service tubing, manufacturers are held to incredibly tight tolerances. We're talking flattening, flaring, hardness tests, and 100% hydrostatic testing. It all ensures that the wall thickness you calculate at your desk is exactly what shows up at the job site.
Next up, pressure and performance ratings and why the material grade changes absolutely everything.
Here's the thing. You can't calculate pressure using dimensions alone. The specific chemistry of the steel is basically the engine driving the performance. Choosing between stainless steel grades isn't just about figuring out corrosion resistance. It directly impacts your yield strength and pressure-bearing capabilities. Just notice how a standard grade 304 pipe boasts a yield strength of 215 megapascals. But if you switch to grade 304L, where the L stands for low carbon, which is awesome for preventing corrosion around welds, your yield strength drops all the way down to 170 megapascals. What does that mean for you? It means a Schedule 40S pipe made of 304L simply cannot hold the same maximum pressure as a Schedule 40S pipe made of standard 304.
We absolutely have to get this right, because out in industrial environments, pressure isn't just some number on a spreadsheet, it's a promise. Maintaining those exact pressure boundaries is a promise of safety in really high-stakes environments, like chemical refineries, volatile oil and gas transports, or heavy-duty hydraulic systems. The dimensional standard guarantees that the steel has the geometric capability to actually keep that promise.
Let's bring it all together now by looking at how to specify pipe like a pro, with some best practices for procurement.
So, knowing all this theory is great, but translating it into a flawless purchase order, that's where the real engineering happens. To avoid any catastrophic sizing or procurement errors, you always want to follow these exact steps. Step 1. Make sure you pair the correct ASTM material spec with its corresponding B36 standard. So for example, if you order ASTM A312 stainless pipe, link it directly to ASME B36.19M. Step 2. Verify your physical dimensions in Table 1 of the standard. Do not guess. And step 3, document that dimensional standard explicitly on your piping and instrumentation diagrams, your P&Is. Seriously, don't leave it up to the vendor to try and guess which standard you met. I actually want to repeat this golden rule just because it is literally the single most common pitfall we see. Never assume interchangeability without verifying the actual physical dimensions in Table 1 of the standard. I'll say it again. Never blindly substitute a 40S stainless pipe for a 40 carbon pipe, especially around that 12-inch mark we looked at earlier, without confirming that the exact wall thickness actually meets your system's pressure requirements.
So we're going to leave you with this final thought today. When you're working with industrial piping, the stakes are just incredibly high. A ruptured pipe isn't a minor inconvenience. It is a profound, life-threatening safety hazard. So the next time you're asked to specify a pipe, are you going to bet your system's safety on an assumption? Or are you ready to crack the code? Open up ASME B36.19M and check those tables. Thanks for joining us for this explainer, and keep on learning.